All right, so I left the last video talking about hydrothermal metamorphism and how the different hot circulating fluids are going to facilitate the movement of the ions near that rock body and overall pretty much change the chemical composition of it. Or not fully, but partly. So this water, these fluids that are involved may be groundwater that percolated all the way from the surface, and when it first flows down, obviously, and then it will get heated by the nearby magma bodies, and it will be driven upward. So it's going to create a convection cell of cool magma flowing down, cool fluids flowing down, and then warmer fluids flowing back up. This tends to occur at low pressure environments, so typically at shallow depths, and usually at low to moderate temperatures. So temperatures need to be high enough for the water to be driven upwards due to evaporation, but not too high so that it's no longer existing. Water that drives metamorphism may also come from igneous activity, for example, as we saw in chapter 4. So in this case is where it comes from igneous activity. It's important in, for example, the vein deposits. So if you guys remember vein deposits, many times these waters that flow through form things such as pegmatites, and within the pegmatites, some of the precious mineral deposits that we have. So the water that is driven from the igneous activity is more water within the minerals themselves, some hydrated minerals, or the nearby rocks are made up of hydrated minerals, and so the water is innate within them, not that it's water from the outside source, if that makes sense. Hopefully that makes sense. Okay, so this type of metamorphism is most common along the axis of the mid-ocean ridge system. So as we have become better at observing what's going on in the ocean floor, we've determined that it is a lot more common along the mid-ocean ridge system, so nearby mid-ocean ridges. So when plates move apart, there's going to be a depressurizing of the system. There's going to be an upwelling of magma that forms the new seafloor at the mid-ocean ridge. The seawater that percolates through the young and hot oceanic crust as it flows downward, being more dense, is later heated by that hot young rock that is percolating in, and it chemically reacts with this new basaltic rock, which causes this hydrated metamorphic rock to occur. So this hydrated metamorphic rock that reacts with the the hydrated, or the fluids, I should say, that cause the basaltic rocks to metamorphose are called serpentinites, or they could be soapstones as well. So those are both two types of metamorphic rocks that arise from the hydrothermal activity related with mid-ocean ridges and basaltic rocks. You will be looking at soapstone in lab, but I don't think that we have any serpentinite samples, but we might. I can't recall for sure. Black smokers, if you guys have ever seen them in videos in Discovery Channel or Animal Planet or something, they're metal-rich fluids that basically gush out of the seafloor as kind of currents, as vents, and they're caused by hot circulating fluids at depth that rise to the seafloor, and upon mixing with that cold water, the sulfide and the carbonate minerals within that contain the heavy metals are going to precipitate from that they're going to precipitate from that flow to form the metallic deposits that they carry. In fact, some of the copper ores that were found in the island of Cyprus are credited to have occurred through this specific mechanism of black smokers carrying those heavy metals within the sulfide and carbonate minerals that make up the bigger mass of it. So the third type of metamorphic environment that we'll check is burial metamorphism. Burial metamorphism tends to occur where there's massive amounts of sedimentary or even volcanic material that accumulate, typically in a subsiding basin, such as the Gulf of Mexico, for example. So you have a lot of sediments that have been buried pretty fast or relatively fast, and so they end up being very thick and they tend to be buried a lot, as the name says. So here you have low-grade metamorphism conditions that might be reached within the deepest layers of this buried sediments. The confining pressure overall that arises and the heat from the geothermal gradient will drive the recrystallization of the constituent minerals within, which changes the texture and sometimes the mineralogy of the rock without causing much deformation to it. Rocks can also get carried to great depths in subduction zones, for example. So that would be the second metamorphism environment that I have listed here. That would be subduction zone metamorphism. In this case, when the slabs of oceanic lithosphere that are a little bit denser than the slabs of continental lithosphere, when these denser slabs get subducted and they descend to great depths, is when you have this type of metamorphism. In these cases, the pressure will increase faster than the temperature because those slabs of sediments and rocks are poor conductors of heat. So they're not very good at conducting the heat at such depths, but they are getting subducted, I should say, pretty fast. So in this kind of cases, you have a high pressure system with not as great temperature system. This process differs from the burial metamorphism that we just saw in the sense that it typically is accompanied with differential stress rather than with confining pressure. So remember, in confining pressure, you have equal amounts of pressure in all directions. With differential stress, there's going to be a specific direction where you have greater stress than in the other directions. So burial metamorphism, you have confining pressure, and with the subduction zone metamorphism, you're going to have typically differential stress, where there is more pressure exerted in one direction than in the others. So regional metamorphism is quite common. It's probably one of the most common ones apart from the contact metamorphism. And it is typically associated with mountain building events. So here, large segments of the Earth's crust are intensely deformed by the collision of two continental crust blocks. So this is what's happening, for example, in the Himalayas. So if you guys remember from the plate tectonics lecture, when two continental plates converge, they will neither one will subduct. They will simply result in mountain building. And with mountain building, there's going to be deformation. These two plates converging, again, result in a lot of mass being thrusted upwards with mountain building, but there's a lot of mass that's also going to be pushed downwards. So with this mass that is pushed downwards, it will experience a high temperature and a high pressure environment, which mostly causes differential stress, or mostly has differential stress, which causes deformation to the rocks. So it is through this type of metamorphism that the shale parent rock progression of the foliated metamorphic textures that we saw earlier occurs. So again, that was going to be from the shale parent rock, you're going to end up getting slate, phyllite, schist, and gneiss. So these rocks end up getting very deformed when they're in mountain building type of environments, basically making all sorts of folds and faults, making things like what you would expect a carpet to look like if the carpet was pushed all the way to the wall, for example. A bunch of rumpled kind of remains. So other less common types of metamorphism also generate amounts of metamorphic rocks, although these amounts tend to be much smaller in quantity than the previously mentioned metamorphic environments. And they also tend to be a lot more geographically constrained, more localized. So we'll go ahead and cover the first one, which is fault zone metamorphism first. So near the Earth's surface, the rocks behave more brittly or more brittle-like. So when they're under stress, they tend to break, which in a fault zone causes rocks to be fractured and pulverized, basically. And again, we'll look at fault zones in Chapter 9. When these rocks are fractured and pulverized, they're going to make this loosely coherent rock, which we call a fault breccia. However, much of the deformation that is associated with fault zones occurs at actually very great depths. And with great depths come high temperatures and high pressures. When the rocks tend to be, deformed at such depths due to faulting, the rocks tend to behave a lot more ductily due to the depth at which they're at. And when I say ductily, I mean kind of plastically. That sounds weird to say, but they behave more plastically. They're able to bend a little bit more rather than break when they're exposed to this stress. So when two sides, for example, of a fault are moving in opposite directions, which is what happens at a fault, it is common for a rock named mylonite to occur. So mylonites are basically gneissic rocks with large crystals which did not get deformed. So these large crystals are typically named porphyroblasts, which again are just large crystals which did not get deformed within the texture that you would expect them to. So these large porphyroblasts are going to make up these lens-like parts of the rock. They make kind of like an eye feature, the eye in your face feature, in a gneissic resembling type of texture. So it is not nice because they didn't get deformed by the same processes of foliation, but two different directions were pulling the rock apart, pulling it apart. And so because of the plastic flow to it, they kind of stretch it in one direction and show some of those crystals not being able to get stretched as much. So they behave in that eye-like structure. So the image on that top right here shows what a mylonite looks like. Okay, and then another type of metamorphism is called impact or shock metamorphism. This occurs when meteorites, which, if you didn't know, are fragments of comets or asteroids that have come into the atmosphere, will strike the Earth's surface at high speeds. In fact, I think that meteorites themselves are the rock that is the remain from the comet or the asteroid once it's at the surface of the Earth. I think it's still considered a meteor if it's within the Earth's atmosphere, and if it's outside, it's just considered a fragment of comet or asteroid, as the name is. But again, you get the idea. Once they hit the Earth's surface at high speeds, they will impact, and that energy of the ones, very rapidly moving fragment is transformed into heat energy. And then from that heat energy, shock waves will pass through the surrounding rock, as you're seeing in the image over here. And it causes a lot of things. So it causes pulverized and shattered material over here, but it also will cause melted rock near it. And at a little bit further spaces from the impact, you're going to have metamorphism to occur in that metamorphic zone. So for example, coesite, which is a very dense form of quartz, is a common mineral to form under this type of conditions, for example.